All right. I think we'll get started as people are still coming in. Just a few of you guys are still not here yet, but so reminder for homework number 4, I actually just extended for one more day. Okay, so you guys can have one extra day to work on. Remember tomorrow you guys should have a SI section. Okay. Don't forget to sign up your SI section for tomorrow if you need help on your homework, okay? Also, please keep in mind that if you need help on your homework problems, you can always let me know. Just email me or set up a Zoom meeting, or maybe come in my office in the afternoon today, Monday afternoon, 1:30 to 2:30. Okay, that's a dedicated in-person office hour. Um, Also, you guys can see me pretty much on Wednesday during the chapel hours. I should be in office, and also Friday. Okay, and then yeah, Monday as well if you want. Okay, so that's on homework. It's due now on Wednesday. Okay, you will have one extra day to work on it. All right. So I did grade your exam number 1. I haven't got the chance to put your grades in the Moodle, but overall, this is what you get as a class in the exam. So 2 of you guys did really perfect in the exam, so 100 out of 100, and then 4 of you guys in the range of 90 to 99, so that's good. Okay. And then majority of, or a lot of them of you guys have between 70 to 79, and then a few of you guys are in the range of 80 to 89. Okay. The rest of you guys, a few of you guys, you probably didn't feel you were doing very well in the exam, but just keep in mind this is only the first exam of the class. Okay, so there are 3 more exams to go, and then as you guys are doing very well in homework so far, and then also in the lab. So your overall grade should be better than what you get in the exam. Okay, so just keep it up. Okay, and then again, now you know how the exam will look like, and then what you are expecting in the exam. So keep just put in some more effort from this point on. So if you didn't do as well as you expect in exam 1, okay, just put more effort, and then I'm sure you guys can bounce back. Okay, so yeah, the average of the class is 72, and then I actually compile what you guys have currently for the lab and then home grade. So the average of the class is still overall is 80% roughly. So that's the class average grade, it's a B at this point. Okay, as I said, this is just first exam, so your grades may be going up later on, or maybe going down, but just keep in mind, okay, that will be changing. All right. So this is why I have. Any of you guys have any questions? All right. So if not, then we'll look at the lecture of the day. So we probably should be able to finish chapter 4 today. Okay, so in the last couple sections here talks about some more forces that you might be seeing often in this class. So last time we talked about weight. So pretty much like whatever object you are dealing with near the surface of the Earth, it will have a gravitational force on it. We call it weight. So weight is equal to mg. So weight is a force, so then it should also have a direction. The direction of it is the same as gravitational acceleration. Okay, so it's pointing downward. So when you look at an object, always remember there's weight of it. Okay, if the object is near the surface of the Earth. And then we talk about apparent weight, which is the perception of your weight, or the force that is given to your body by the surface of contact of your body. Okay, so that's apparent weight. one example is if you are riding an elevator, the moment the elevator just moves up or moves down, or when it slows down, you will feel different apparent weight, okay, than your actual weight. All right, so we'll be looking at one of the new forces today called normal forces. Okay, so normal force, according to its definition, it's the force that is due to two objects in contact. So then one object will be exerting the force on the other object. That force is called normal force. Okay, so it's the force exerted by a surface on the object. Okay, so for example, if you have an object sitting on the table, then there's normal force on the object, okay? And then also like if you have an object on the floor here, there's normal force on the suitcase here, okay? If you look at the free body diagrams of the first figure here, if you are looking at this cam here, so you will have weight, you will have a normal force. So then when you draw the free body diagram, you want to indicate both forces, okay? So the normal force M and then the weight W, all right? And then for this figure on the right here, when you look at your suitcase here, less weight of it, less normal force, okay? That by the surface to the suitcase. And then there's this pulling force, okay, F, all right? So that's your free body diagram. And then you probably notice that this F is resolved into two components. It's X component, Y component. Okay, so that's what you do when you have forces in two dimensions. You want to resolve them in X and Y components if they are not already in X and or in Y components. Okay. All right. Now the reason that this force get the name of normal force is because that the force that is always pointing in the direction that is normal to the surface of the contact. Okay, so then that's why it gets the name of normal force. Okay, so it's perpendicular to the surface or in the normal direction of the surface. All right. So if you are in an inclined surface over here, then the normal force is perpendicular to the surface of contact. Okay, so in the normal direction in that way. All right. Okay, so let's take a look on one exercise problem here. All right, so it says find the normal force exerted on a 2.9 kilogram book resting on a surface inclined at 36 degrees above the horizontal. Okay. So let me see. Um, Let me put you guys in breakout rooms again, okay? So you guys can work and have discussion together. I realized last week that some of you guys might be in a place that it's not like you're not able to talk. So let me just put less breakout room so that you might have more people in the room in case if one or two of you guys are not able to speak, then the rest can be still speaking up, okay? And then if you are not able to speak, you can chat typing, okay? So let me do that. Let me just have 6 rooms, so then in a room you will have 5 or 4 of you guys in there, okay? So let me create this and then open it. All right, I think you guys are all back. So yeah, I think I forgot to mention that you can submit your responses online. So I saw a few of you guys actually did that already, okay? But let's take a look on the solution together here. I'm going to stop sharing screen so then um, the camera review will be zoomed in here. So this one says you have a 2.9 kilogram book resting on a surface inclined at 36. Okay, so I just started scratching like this. So this is my book over here. The first thing I want to do is I want to it asks us to find the normal force. Okay, so but the first thing I would like to do is to draw all the external forces on this book. Okay, so for the first force to consider, as I mentioned, because we are near the surface of the Earth, so we need to consider the weight. Okay, so W, that's the weight, and then it's always equal to mg. Right? It gives out the mass 2.9, so then the weight you can calculate, okay, by doing 2.9 times 9.8, okay? Now, because the book is in contact with the surface, inclined surface here, so then there will be a normal force on the book in the normal direction of the surface, okay? So then we call it normal force, okay? So you can see, so it's obviously, or maybe it should be kind of obvious to you, okay, that these two forces should be acting on the book, okay? Now the question is there additional forces here? So if you look at these two forces, they are not in the same dimensional here or the same direction, same line, okay? So you will probably figure out that then these two will not balance out, okay? So in order for two forces to balance out, they should be in the same line pointing opposite to each other, right? So then if you just think about these two forces, then there must be another force to balance out this guy, right? So in this case, would be the friction force we haven't talked about here, but or the friction force, okay? So there should be a friction force here, all right, to balance out these two forces, okay? Because otherwise this book will move down, okay? So by examining the scenario here, you will realize that these are the three forces acting on the book over here, okay? So that's your free body diagram, all right? Now, if you are taking the steps of coming up to free body diagram, you probably realize we need a coordinate system, right? We need an X and Y. So normally we'll do X in the normal direction and then Y in the vertical direction, okay? So this is normally what you would do. So if you take that as your X and Y coordinate system, then you will realize, okay, so then weight is in the negative Y direction, so weight is fine. But for these two forces, then you'll have to resolve them into the X and Y components, right? So in this case, it will be easier for you to choose the X along the inclined surface and then Y to be perpendicular to the inclined surface in that way, okay? So you will not do that way, but you will do this way, because in that case, then you have two forces, either they are in X or in Y direction, but just one force that is not in X and Y direction. Then you will just need to resolve this only force into X and Y component, okay? So it's easier to resolve one force into the components than to resolve two forces into one component, or one into their components, okay? So this is what we will be doing when you have an inclined surface for most of the time. Okay, so if you have inclined surface, then you will take X along the inclined surface and Y to be perpendicular to it. Okay, we did this exercise in lab 3 in vector. The second exercise, additional exercise problem, where it says if there's inclined surface, then you can actually set a new XY coordinate system. Okay, so that's what we are going to do here on this one. So now you need to resolve this into X and Y. Okay, so then this is its Y component, and then this is X component. Okay, so to resolve a force in the component, you basically put the projection of the force into the X and Y, okay, to give you its X and Y component. All right, so once you have done that, then you are going to cross out this force, so then you don't look at it again, because now this guy now becomes two forces, okay, or the two components, okay. So if it's better for you to cross it out, so you don't have to repeatedly consider that one, okay. So then it's two components. Now let's look at the geometry here. So this is the inclined angle theta of 36 degrees, okay. So then according to geometry, this guy here should be also the 36, okay. So this is the 36 degrees of theta, okay. So then in this case, the x component of the weight, we can call it Wx, will be this guy here, Wx, okay. And then this guy to be Wy over here, the y component, kind of writing them all together, but x is the x component. So that should be, you can see the weight, right, times sine of the theta of the 36, okay, or you put mg sine of theta, because weight is equal to mg, okay. So this is the x component. Then the y component will be mg cosine, okay. So this is the y component adjacent to this angle, so y cosine, y equal to mg cosine, okay. So you resolve the weight into x and y component, all right. Now you have four forces here on the object. They are in x, two of them are in x, two of them are in y, okay. But you also want to indicate the direction here, because in x component, this is pointing to the negative x component, okay. So then you probably want to say minus over there. Then here, the y component is in the negative y direction, so you also want to indicate that's minus mg cosine, okay. All right. So now let's take a look here. We are looking for this normal force, all right. So this one will balance out the y component over here, okay. So then if you look at the y component here, the net force in y component, okay. So for two-dimensional problems, you'll be looking at the x component net force and then y component net force separately, okay, from free body diagram, okay. So because we are looking for y, so we'll just write y first. Or if you like, you can say, okay, I'm going to look at x and then y separately, looking at them together. So in the x component will be the friction force, which is in the positive direction, minus the Wx would be mg sine theta, okay? And then in the y direction, you have the normal force, and then the y component of the weight, so it'll be the normal force minus the y component mg cosine of theta, okay? So these are from your free body diagram. From Newton's second law, in this case, because your book is resting, that means it's not moving, so then the net force should be equal to 0, okay? And then net force in y should be also equal to 0, okay? So when you have an object that is resting, that will tell you its net force is equal to 0 in x direction, and then net force is equal to 0 in y direction, okay? If it's not moving, all right. So now let's take a look. We are looking for normal force N here. So then you'll be looking at this. So normal force should be, net force in Y should be equal to M minus that guy. And then the second law will tell you net force is equal to 0. So you can set that this equal to 0. So M minus mg cosine theta should be equal to 0, right? So then your normal force should be equal to mg cosine theta, okay? So you can see that you know m, you know g, you know theta. So you can calculate for your normal force to 2.9 kilograms times 9.8, okay, meters per second square, cosine of 36, okay. So that gives me 23, all right, roughly 23. It's 22, actually 22.99 newtons. So we can keep two digits as 23 newtons, okay. Any questions you guys might have on this one? So I think this is the one that we actually the first time we look at when they um, two-dimensional, okay, forces here, and then combine with Newton's second law. Okay, so it's similar to one-dimensional. One-dimensional, you just look at net force in one-dimensional. Now you in two-dimensional, you break them into two dimensions. Okay, so then you'll be repeating that Newton's second law and free body diagram analysis. All right. So if you guys have no questions, we will move on. But in this case, you probably realize that there's additional information we can utilize. Okay, so there's an X component we didn't use. Okay, so if you were asked to for what would be the friction force, then you can use that X component of net force. Okay, from free body diagram and the Newton's second law, you can set the two equal to each other. Then you should be able to solve for the friction force in that scenario. Okay. All right. So we're going to move on here. So the next force you might encounter often in physics is called tension force. So tension force is basically force exerted by a rope, a string, okay, when and then become taut. Okay, so if you pull the string, you will feel like the string is pulling back on you. Okay, so then the force exerted by the string is called the tension force. Okay, and so in real scenario, okay, the tension may be varying at different locations of the string. So for example, in the figure shows here, if you have a crate attached to a rope, which is attached to the ceiling on the other end. Now, if you look at three different locations, one at the lower end, and then the middle of the rope, and then the top of the rope here, you probably can realize that the tensions at those different locations should vary slightly, right? Because at this point, this tension should be just equal to the weight of the rope of the crate, okay? So then the crate, the tension and then the weight of the crate balances out on the crate, okay? Now at the middle part here, the tension should be equal to the weight of the crate plus the weight of the lower part of the string of the rope here, okay? Because in reality, this rope have some small weight or mass. Okay, so in this case, T2 should be slightly larger than T1. At the top point here, T3 then would be again larger than T2 because then T3 would be equal to the weight of the crate plus the lower part of the rope and then the top part of the rope. Okay, so then T3 will be larger. But in this class, okay, if you are not otherwise told, we'll consider that tension throughout the rope or string to be uniform. Okay, we'll assume that the string or rope has very negligible masses. Okay, so then we don't have to worry about that small variation in the tension throughout the rope or string. Okay, so unless otherwise stated, we will take assumption that the string is massless or it's having negligible mass. Okay. All right. So this is tension force. And also, if you have when we use rope, sometimes we use pulley in addition to use rope to form simple machine. Okay, so for example, to pull up a crate like this, you can put a pulley over there. So then you can lift the crate up. Okay, by that in that way. So in that case, all right. So if again, we are going, if there's a pulley involved in the problem, we are going to assume that it's an ideal pulley. That means it just changed the direction of the tension force. Okay, because when you're pulling in this guy over here, now the tension is pulling in that direction, but on the other end, the tension is pulling in that direction. Okay, you just change the direction of the tension, but tension in the rope again, throughout should have the same magnitude, okay? All right, so those are the assumptions when we encounter a pulley in the system. All right, so we will take a look on this one. This one says, suppose a 60 kilogram gymnast climbs a rope. What's the tension in the rope if he climbs at a constant speed? And what's the tension in the rope if he oscillates upward at the rate of 1.50 meters per second squared? Okay, so again, in part A, it says the gymnast actually climbs up at constant speed. All right, so that means the velocity is constant. Okay, it's going up and then constant. So when velocity is constant, that means velocity is not changing. All right. If you see that, then it means that there's no oscillation on the object. Okay. So I'll give you guys a couple minutes here to solve for this one. This time I will not open the breakout room, but you guys can work just by yourself on this one. And then you can submit your answer if you have it. Okay. We'll take a look at the solution in a few minutes here together. All right, I'll wait another minute before we look at the solution together. Okay, you can continue submitting your responses online. All right, so let's take a look here together. So I just did a brief, very simple scratch here. The gymnast here climbs up the rope here. So to look at the free body diagram on his body, we'll use the dot to represent his body, and then there will be a weight on the body. There will be tension in the that direction. Okay. Now, when it says velocity is constant, okay, so you immediately, or is equals to constant. Sorry about that. So then you immediately realize, okay, then acceleration is equal to constant is zero. Okay, so that means no change in velocity, acceleration is zero. All right. So again, we will be looking at the free body diagram here. So then realize that there are two forces. If you pick upward to be positive, the direction, all right, you can say y or x, whatever you want, because this one, this time, it's just one-dimensional problem. Okay, so you can realize that net force, okay, it's going to be from the free body diagram, it's going to be equal to T minus W. Okay, T is in the positive direction, W is in the negative direction. Okay, so this again is from your free body diagram. And then according to Newton's second law, the net force should be equal to mass times acceleration. Okay, so acceleration is zero, so then net force is zero. Okay, so this is the first from, this is in second law. Okay, so then you are looking for tension in the rope here. So you'll set the two equal to each other. Okay, free body diagram tells you net force is equal to T minus W. From second law, it tells you net force is going to be equal to zero. So then T minus W is going to be equal to zero. So your tension should be equal to W, which is mg. All right, it tells you 60 kilograms times 9.8, the G. So then it should be 688 newtons. I see all of you guys got this right when you submit your responses. Okay, so that's part A. Now part B says if the acceleration, if let's say an acceleration, okay, of 1.5. So in this case, everything else is the same. Net force again from the free body diagram should be tension minus W. Net force from the second law, now this is equal to m times a. This time it's not equal to zero. The acceleration is not equal to zero. Okay, so then you realize that T minus W is equal to ma. So then T is equal to W plus ma. Okay, which is mg plus ma. All right, or mg in the previous one is 6688. You can just write it down, or you can plug in 60 multiplied by 9.8 plus the 60 multiplied by 1.5 meters per second square. Okay, so then that tells you this is going to be 678 newtons. Okay, I see most of you guys got this one right as well when you submitted your responses. Okay, questions you guys might have before we move on? All
How
right.
does
If
the value go
yeah,
down from 688?
I'm sorry, it's 588 for the first one. That's it's my mistake. The
Okay.
588. Yeah, good point there. Yeah. All right. All right. Okay. So then we can move on to the last section of this chapter. So we have solved or look at several examples up to this point. Okay, so from the last lecture and this one, so we can kind of summarize what would be the strategies when you solve problem with force and Newton's second law. Okay, so the step one is again usually that's what you want to do first is to identify the physical principle involved. Okay, so in this case, or in the cases we have been looking for in the previous lecture, and this one we are pretty much dealing with Newton's second law. Okay, um, so that's first step. Second step is um, identify what needs to be determined and what's known or can be inferred from the problem. So as you can see from time to time, that a lot of times you can actually get more information than when you just read the problem at once. Okay, so when you set up your coordinate system, that might give you extra information, and then when you read carefully, it will give you extra information. Just like RA here, when we read that velocity is constant. Okay, so that actually translate as acceleration is equal to 0. Okay. Um, Step 3 then is to draw the free body diagram, of course, and then apply Newton's second law. Okay, to solve the problem that was Newton's second law. So when you draw free body diagram, you will treat the body as one point, and then draw all the forces, all the external forces on the body. Okay, and then from the free body diagram, you can tell what's the net force in x direction, and then one net force in y direction. Okay, and then you can set up Newton's second law in x direction, which tells you net force in x direction is going to be equal to mass times acceleration in x direction, and then net force in y direction is equal to mass times acceleration in y direction. Okay, then you can set the two up. Okay, to solve for your problem. All right. Um, Now, as I mentioned, so I probably will not go through the examples already in the textbook because they have detailed solutions to it. I just want to give you different examples in classes, so then you get exposed to many different examples. Okay, so but do check those examples in the textbook, especially this 4 examples. Okay, they will give you ideas on how to solve problems with Newton's second law or Newton's law of motion in general. Okay. Um, so at the end, I'm going to just show you guys one more example here. So I'll have you guys take a look on this one first. I'll give you a couple minutes to try maybe to solve it by yourself or come up with a plan. So then in about 2 minutes or so, I will show you the solution. Okay. So it's okay that you couldn't figure out the answer in 2 minutes, but at least you can have an idea what this one is asking and then maybe come up with some plan. Okay. All right, so we'll take a look on this one together here. So in the fire rescue, it tells us the person's weight mass is 60 kilogram. Okay, so when that's in kilogram, you realize that's mass. Okay, um, so you will see that there will be weight of the person. All right, it should be acting on the center of mass, but because when you are doing a free body diagram, we can represent the body as one dot here, so it doesn't matter. I can just say over here because these two forces are acting on this point. So it'll be easier for me just remove the only weight up here. Okay, so let's say this is the weight, all right, and then that should be equal to mg. There's this rope here extend in this direction and that direction. So there should be one force here, one force there. Okay. Now there's this T1, which I probably have it a little bit too long, but let's say this is T1. Okay, so forget about that one. And then there's this T2 here, kind of like that one. Okay, so forget about those two. In this case, we can take the x direction to be horizontal, y direction to be along vertical direction. Okay. Now in the previous case, when we have inclined surface, we say it's easier to have x along the incline and y perpendicular to incline. So in that case, you indeed have the two forces already along. One is along the surface, one is perpendicular to the surface. So it's easier to set up the coordinate system. So you have two already in either x and y direction. But in this case, these two forces are not perpendicular to each other. Okay, so it's not actually possible to set up a different coordinate system than normally horizontal as x and vertical as y to make the problem solving easier. Okay, so then we'll stick with the normal x and y coordinate system. Then we'll have to resolve this guy in the x and y component, and then this guy in its x and y component. Okay, so there will be this x component of T1 and then y component of Ty1, Tyx, and then there will be this T2x, and then over here, T2y, the y component, all right? Then once you have resolved them in x and y component, you don't want to cross them out so you don't double count on them all the time. All right. So now you have your forces in x and y direction. Okay, from the free body diagram, you can write it out that so in x direction, net force is going to be the T2x minus T1x because those are the forces in the x direction. Okay, so T2x minus T1x. In the y direction, net force is going to be equal to, now in the y direction, there's T1y, T2y, and then there's this weight. Okay, so you want to add T1y plus T2y minus weight, which is mg. All right. Now it says momentarily, she's motionless. So that means she's not moving momentarily. So then that means x, acceleration x and acceleration y, they are both 0. All right. So this is from, these two are from free body diagram. And then again, from second law, you can write the x component net force should be equal to max, y component net force should be equal to may. All right, and then realizing that ax and ay are 0, so these two are equal to 0. Okay. All right. So now we can set up that T2x minus T1x equal to 0. Okay, combine the net force in free body diagram with the net force given by Newton's second law. All right, and then combining this guy, free body diagram in y component with the second law in y component. And then the T1y plus T2y minus mg also equal to 0. So you'll write up those two equations, all right? Now you are looking for T1 and Ty, all right? So how do we relate T1 and Ty here? Because we are given the angles here, we can write their components in relation with the magnitude and then the angles, okay? So T1x, you can write this, looking at the geometry here, this is the 15 degree. So then this is 15 degrees. So T1x will be T1 sine of 15 degree, okay? And then T1y will be, this is y here. Now this is 15 degrees, so that means this is 15 degrees. So it will be T1 cosine 15 degree, okay? Similarly, you can do the same for T2x and T2y. So T2x over here, this is the 10 degree adjacent to this side. So it will be T2 cosine 10. T2y will be, this is 10, so that means this is 10. Okay, so then it will be T2 sine 10. Okay, all right. So then you can write the components into the magnitude times the angle, sine or either sine or cosine. All right. So in that way, so now this equation becomes T2 cosine 10, the first one, T2x minus T1x, T1 sine 15 goes to 0. The second one, T1y will be T1 cosine 15 plus T2y will be T2 sine of 10 minus mg. You know m, which is 60. All right, g is 9.8 equals to 0. So you have these two equations, and then you have two unknowns in them. Okay, T1 and T2 are being the unknowns. So you should be able to solve for T1 and T2 by using these two equations. Okay, so we are going to, from the first equation, we are going to write the one unknown in terms of the second. Okay, so we'll be doing like T2, because this minus this equal to 0. That tells you this guy equals to that guy. T2 cosine equals to T1 sine 15. All right. So then you can write T2 in terms of T1, basically divide both sides by cosine of 10, gives you T2. All right. So T2 is equal to this. And then you can plug this expression into the second equation where you have T2. T2 is going to be replaced by this expression. Okay. So in the second equation, you are writing T1 cosine of 15 plus T1 sine of 15 over cosine of 10. So this is T2, okay, T2 sine of 10. And then minus this equal to 0, or that equals to this guy, 60 kilograms times 9.8 meters per second square. Okay, you can move this term to the right, so then that equals to that. All right, so next you are going to single out T1, right? So then T1 times cosine of 15 degree plus sine of 15 over cosine of 10 times sine of 10 equals to, let's multiply by that, okay? Which is, I think, 588. That's what we did earlier in the previous one. Then divide both sides by this guy, will give you T1, okay? So then T1 is equal to, if you did that, T1 is equal to 581 newtons. Okay. Once you have T1, you can take T1 back in there to solve for your T2. So then T2 is equal to 581 sine of 15 over cosine of 10. All right. So that will be 153 newtons on that guy. Okay. All right. Questions you guys might have?
What time is that SI again?
10:20 Tuesday in Rome, region 14. And then you guys want to sign up first, okay? All right. So if you guys have no question, then we'll stop here. for today. Okay, I will see you guys on Wednesday. Bye, guys.